Chapter 19, Chemical Thermodynamics. Chapter 19 answers the question, will something be spontaneous or not? Spontaneous means that it will happen all by itself without any outside intervention. Chapter 19 gives us pieces and mathematics to help answer that question. So the first thing it says is this reaction process going to happen, reaction or process going to happen by itself or not? And there are two driving forces that make this happen. One you've already learned way back in chapter 5. You learned that reactions or processes contain an amount of enthalpy, which is an internal energy or a heat at constant pressure. Generally, things that are exothermic are more possible or will more likely be a driving force to make a reaction or a process happen. Things that are positive and therefore endothermic generally, but they could be a reaction or a process that happens spontaneously, but maybe not necessarily as much as something that's negative. But this is only one piece. The other piece you actually learned about when we were talking about solutions, and this piece is called entropy. Entropy is symbolized by a triangle and then an S, and the triangle of course means change, and S is the symbol for entropy. Entropy is a fancy name for the number of microstates possible for a system. An unfancy way of saying that is the randomness or disorder or the mixed upness of a system. When something has more entropy or the entropy number is larger, that means it's more mixed up, more random, more disorganized. There are more possible states for a system. So for example, something that like frozen water or ice would not have that many places for the water molecules to be. Whereas something like gaseous water, those molecules or those particles could fly all over the place and have lots of distance between them. And so those would be much more random or much more disorganized or much more mixed up. And so we'd say that they have many more possible states for that system in the gaseous phase. A negative sign for it means it's more organized, more ordered, more arranged. And so a negative entropy change would mean that something became more organized. When entropy is positive, it means that there is more possibility that a reaction will happen. Just like when H is negative, it's more possible that a reaction will happen. Well, just when S is positive, things are more possibly disorganized. There's more possibility that a reaction will be spontaneous and occur. Chapter 19 is the study of this delta H and delta S interactions. It explores how these two forces right here drive whether something will happen spontaneously or not. Let's take a closer look at S, at entropy, before we get into the interaction of these two to answer the overall question of chapter 19, spontaneous or not. So first of all, I already gave this example. Things that are solids have less entropy versus things that are liquids versus things that are gases. So there are more microstate possibilities as you go from a solid to liquid to a gas because the particles become more mixed up, more disorganized. If something is a gas only, like there's a change from one type of gas to another, generally the rule of thumb is the more gas molecules you have, the more randomness or more disorder or more microstates that are possible. This makes sense because the more types of gas particles you have, the more organized or randomness there could be between them. So looking at entropy a little bit closer, let's look at relationships that make entropy increase or decrease. First of all, entropy increases from gas. Entropy increases when you form a gas from a liquid or a solid. So a change from melting, obviously, to a liquid would increase the entropy, or going from liquid to a gas. When something is a solution or forms from a solid being dissolved in a liquid, then you would increase the amount of entropy. You would increase the amount of microstates in that system. Or thirdly, the number of gas molecules increases. In a process, if you take and you have one type of gas molecule and it breaks up into two or more, then you would say that the entropy increases as that change occurs. Let's look at some example problems, and I have a copy of a page from your textbook. If you're in the 13th edition yet, this is from page number 826, and we're going to zoom in on just a few of these questions to try to make these pieces make a little bit more sense. So let's look at the first process here. We're going from H2O liquid to H2O gas. What will happen to the entropy change? Will the S be positive or negative for each of these processes? And we just talked about when you go from a liquid to a gas, the particles spread out or move further apart from one another. There's more possible microstates, and so we'd say that the delta S is positive, or the change in entropy would be positive for this to go from a liquid to a gas, because there's more microstates or more possibilities or mixed upness of a gas than a liquid. Here we have an aqueous cation and an aqueous anion, so we have two solutions going to a solid. And as we know that if you form a solid, those pieces or those particles will be in like set organized arrangement versus aqueous where they're dissolved. And so here we'd say that it would be becoming more organized, and so entropy would be negative. We'd say that the delta S would be negative because we're going from a lot of microstates to a few less over here. Nextly, let's look at, we have 4 solid ions and 3 gaseous oxygens going to 2 solid particles over here. And so we're going from a solid and a gas to a solid only. Now obviously gases have much more entropy than do liquids or solids, and so going from a gaseous piece on this side, even though there's solids over here, to only solid means it's going to become more organized as well. So once again we have a negative entropy because we're becoming more organized and only have a solid on this side of the reaction. In this process we have a gas and a gas going to 2 gases. And so if you look back at your notes, what happens if the number of gas particles increases? Well, then the entropy increases. We have 1 mole of gas here, 1 mole of gas here, and we have 2 moles of gas here. And so from this side to this side, we go from 2 moles of gas to 2 moles of gas. Oh, it's not really changing. So this one would be a really difficult one to predict. As a matter of fact, we might even say that the entropy is so close, we'd almost say that the change would be almost 0. There's almost no change in the entropy at all. Let's see if we can predict the sign of S. I'm going to pause a little bit along the way here, and we'll see if you can predict the sign, and then I'll answer the question to see if you've got the sign of S appropriate. Here we're going from H2O solid to H2O liquid. Positive or negative for delta S? Hopefully you predicted that there is much more randomness and disorder in a liquid because the particles can slide over one another than you can in a solid, and so you'd say that the delta S is going to increase, and so it would be positive for this process. Carbon solid plus oxygen gas goes to CO2 gas. Okay, so you'd say I have 1 mole of gas here and 1 mole of gas here. That's great. Those are equal, and we'd almost predict 0. Whereas here I also have 1 mole of solid. This would be more arranged over here in the solid phase, and that goes into the gaseous phase. So I would guess that it probably would be small, but we would probably also be increasing the entropy. Last one, increase or decrease in entropy. From this side, we're going from 1 plus 3 or 4 moles of gas. To this side, we're going to 2 moles of gas. And going from 4 to 2 means we're decreasing the number of possible moles of gas. So we're decreasing the number of microstates. So we'd say that entropy would be negative in this case because it's becoming a little bit more organized. This is a good time to pause and just give reminders to the laws of thermodynamics. The first law of thermodynamics we learned way back in Chapter 5, and that's the conservation of energy, that energy is not created nor destroyed, it's just transferred from one place to the other. The second law of thermodynamics is one we learned in Chapter 13, but we'll remind of ourselves right now, and this says entropy is always increasing. So throughout the universe, the entropy is always getting larger. We'll pick up with more ways to find entropy and how much it is in our second video cast.